questions of quiz 2. Yeah. Some students ask me these 3 questions, and they are relatively hard. Yeah. Let me explain one by one. Yeah. The first one, hint for question number 6. Yeah. All right, so let's look at question number 6. This one, suppose an n-element array with n greater than 2 is unordered. Okay, unordered. What is the minimum number of inversions in this array? First, you need to know the inversion meaning, right? Inversion meaning. Yeah, the definition is given in the notes. Yeah. So basically, here, when we talk about inversion, we look at a pair of 2 elements in the array. Okay, all right. 2 elements we take from the array using their natural order. Okay, yeah, here. This one using the natural order, that means the subscript I should be less than the subscript j in their natural order. All right. Then, when we look at the value should also be in ascending order. Ascending order. Then, because that's the in order case, right? In order case, in order case, then we do not worry about it. Yeah, because here the goal is sorting. Here, when we use this inversion, the goal, why we define inversion concept? For sorting. Because if it's in order case, then we do not need to do sorting work, right? Already in order, why we need to do sorting work? Only when it is not in order, then we need to do sorting work. That's the reason we introduced this concept. All right. So that is the out of order case. Out of order case, so that is a sub I greater than a sub j. This is, we say it is an inversion. Okay, all right. Yeah. So that's the meaning. All right. So from the given question, we need to find a minimum number of inversions in the array if array has the condition n greater than 2 and unordered. First, this unordered condition is useful. Yeah. It tells us the minimum number cannot be 0. Right? Yep. If minimum number equals 0, then it is ordered. Yeah. Right? If the minimum number, I just write a minimum number, right? And not confusing, minimum number of inversions equals 0, then the conclusion is ordered. For that reason, the minimum number should be greater than 0. Okay? Yeah, the answer. All right. But next, minimum number of inversions. Here, I may like to give you, 2 versions, 2 similar versions. The version 1, this is the version 1. Okay? for comparison. This is version 1. This version 2. Okay, all right. Condition is the same as given in this question, yeah, but the question is different. Version 2 question, yeah. What is the minimum number of elements? Yeah, here, not inversion, elements that are not in place. This question, okay, version 2. Now you can see version 1 and version 2, the questions are different, right? Version 2 and version 1, although they are closely related, but the answers should be different. Here, I ask you the minimum number of elements, not inversions. Okay? Inversion, one pair, that is the one inversion. Elements, that one pair of inversion, there are two elements. Okay? So the answer is different. All right. Okay? Yeah. But when you answer this question, you need to answer the version 1 question. Do not answer version 2 questions, because it's very likely some of you may answer the version 2 questions, not version 1 questions. Yeah. Even I myself, I got confused. All right. Yeah. I made this question, but sometimes I use version 1, sometimes I use version 2, and I myself, I could get confused. Yeah, actually for this one, I did confused. Yeah, the first time when I entered the answer, I entered 1 for version 2, but later I changed. That could impact your answer. All right, but if your answer is affected by that change, I will correct it. Okay, so here I write it down. Okay, I will correct the wrong answer, or I will correct what wrong grading. Yeah, because for that reason, you may get a wrong grading. Okay, problem. After I show you the answer, yeah, later I need to open up the answers. So when you see the answers, look at this question. If you did it correctly, but you didn't get the point, then I will give you the points back. Okay, the 4 points back. Yeah, yeah. I can check your answers. Yeah, I think I can find some place to see your answers. If I see you entered correct answer, but you didn't receive the points, then I will give you back. Okay, so that is this question. All right, yeah, clarify this question. Okay. All right, so next question, hint for question 8. This one, yes. Some students, do not know how to find the answer. Here it's a simple question. You are only given 4 elements, right? Yeah. In this format, so the question is, how many inversions? You need to count the number of inversions in this small array. Okay. Yeah. But most of you may have the question, you cannot find all the inversions. You can find some of inversions. The questions, how to exhaust all the inversions. That's the main question. Okay? How to exhaust all the inversions. All right? Yes. Here, oh, what's wrong? Yeah, here. Here, 4, 2 is an inversion. Right? Because not in order, right? 4 greater than 2, not in order, yeah, or in descending order. Yeah, here it's in descending order, so it's an inversion. Okay, yeah. And 2, 3, ascending order, not an inversion. Okay, yeah. Just before we start, just clarify, yeah, because I'm afraid some of the students still not get to this point. Okay, so all right, but my main explanation is focused on do the counting, how to do the counting to exhaust all the inversions. Okay, all right, but I cannot solve this problem for you. I need to let you know. I need to let you solve the problem by yourselves. Okay, yeah. So here I only talk about a general array. I do not work on this array. I talk about the general array and how to do the counting in the right way. How about that? Okay, all right. So we have for the general array, we have a 4-element array in this way. Okay, yeah. X1, X2, X3, X4. Oh, too sensitive. Like this. Okay. Now do the counting. Okay. All right. Case 1. Yeah. I do it using a few cases. The goal, I try to cover all the possible pairs. Now here, let me write the goal. Goal, we need to cover all the pairs. Do not miss anyone. Then after that, then you do the counting. Case 1, all the pairs start with X1. How about that? X1, X2, pair number 1, X1, X3, pair number 2, X1, X4. Okay, so we only have 3 pairs in case 1, starting with X1. Okay, yeah. Sometimes I like to call this X1 as the anchor. The anchor is at X1. Yeah. Whatever, because that's related to the view. In which view you are taking. Yeah. All right. Yeah. That's not important. Okay. Yeah. Here. With these 3 pairs, can you examine one by one which one is inversion, which one is not? Okay. So if it is inversion, you check it. Okay? If it's not inversion, you put a cross sign. Inversion, you check it. Okay. Then the answer, how many? Yeah. So you get that number, right? Yeah. Then case 2, this time the pair should start with x2, or we use x2 as the anchor. Yeah, x2, x3. Okay, all right. Do not include x2, x1. Okay, because that's not a natural order, right? x2 comma x1, this pair does not appear in the array in the original appearance order. Okay, yeah. So we do not include it. All right, x2, x3, x2, x4, only two you need to consider, because x2, x1, you should not consider it, because you only consider x1, x2, but you do not consider x2, x1. Okay, yeah. In these two, then checking. First one, inversion or not. Second one, inversion or not. Yeah, so then you can get a number of inversion for this category. Yeah, case. Yeah, let's say case, because it's not that big. Okay, yeah, we do not use that big word category. It's a case, right? All right. The last case, case number 3, the last case. Yeah, here I put the anchor element x2. Okay, the last case anchor element 3 comma x4, only one case. Yeah. Is it inversion or not? You get another number, counting number for the number inversion. Then you add them up. Okay, 3 numbers adding together, you get a total number of inversion. How about that? Because in this way, you won't miss any inversion in the given array, because you cover all the possible pairs. And for each pair, hopefully you can examine if it is an inversion or not correctly. Okay? In order or out of order, ascending order or descending order. Descending order, it's an inversion. Ascending order, it's not an inversion. Okay? Yeah. All right. That's this question. The last one I like to explain, hint for question number 10. Yeah, this one, yeah, because this one is a concept understanding. Some students, got confused. Yeah, because here we compare the algorithm's efficiency, performance, well or not, when the problem size is relatively small. That one. Okay. Yeah. The first question I like to clarify based on intuition. Yeah. Intuition. Yeah. Many students may have this intuition. Okay. Yeah. May have this intuition. So their logic, reasoning, or intuition, or common sense, whatever, may look like this. Okay, yeah. Yeah, let me just write the meaning in a short way. Yeah, so here, in this way, the faster algorithms are likely faster, yeah, for smaller problem sizes. Okay, likely, all right? All right, yeah, that's the intuition. Think about it. So do you believe this or not, right? Yeah, think about that. Or at least it comes from some natural understanding, right? Yeah, okay, yeah. But I like to clarify things, with a little more background to help you answer this question. Okay, likely, this word, yeah, not quite rigorous, right? Yeah, likely, yeah. There could be some exception, right? Although you say likely, but still you allow exceptions, right? Yeah. But here I like to point out another important fact in our real world programming. Okay, yeah. So that's this. You will have this kind of experience more and more later. So that is, in order to get a faster algorithm, we may, yeah, here I just, use this word may, we may spend more time to do preparation. To do preparation, okay? Yeah. This part, many times we call overhead. Overhead part. You need to spend time to do preparation. Yeah. Because the faster algorithms are not free, right? The effort, you need to pay more effort to get a faster algorithms. Okay? So some of the effort is reflected in this preparation part. And sometimes we just call, overhead. Okay, overhead part. Spend more time to do preparation as the overhead part. Okay? And as a result, as a consequence, and the performance gain from the smaller problem sizes may not be able to overcome the overhead. Okay? You may have some performance gain, yeah, but for smaller problem sizes, even you have some performance gain, that's relatively small, right? Yeah. Okay. Yeah. That small gain, think about this. That small gain cannot overcome the overhead part. Think about that. Okay. Yeah. But for larger problem sizes, then because your gain is huge, Think about that. Your gain is huge, but the overhead part is not that big. The overhead part usually fixed. The overhead part, you do preparation, that cost is fixed. Fixed, that means when you increase the problem sizes, that overhead part is not increased. Yeah, you pretty much use the same amount of preparation time. Yeah. Then your huge gain can overcome the overhead part. Think about that. That, behavior, okay, typical behavior, right? Yeah. So this is, let me call the overhead view, okay? Yeah, we understand this question with this overhead view. Yeah. But I also like to give you another view. Yeah. Another from asymptotic. Yeah. Let me write the correct spelling. Asymptotic. Asymptotic notation view. Yeah. From asymptotic notation view, we can also see this point. Now, here I do not write the whole definition, but because it would take too long. It's not necessary to write a whole definition. Yeah. Here I just write the relevant part. I just write the relevant part, related to this question. The relevant part. So here, let's look at the big theta notation. Okay, yeah, big theta notation. Yeah, the relevant part. Remember we need to find the C1, C2, two positive constant, C2 for the lower bound. Yeah, so here, when we describe this asymptotic notation, we can find a positive C2 constant, C2 multiple of G of n greater or equal to F of n, less than or equal to F of n, and less than or equal to C1 multiple of G of n, okay? Then, after that, there is another important condition. For all n greater or equal to m of 0, m of a 0, okay? Yeah, yeah. This number, n0, and I explained it corresponds to when n is sufficiently large. Remember that? Sufficiently large, okay? So why we have this condition? This condition tells us we can skip relatively small sizes. How about that? This exactly tells us skip some small, or precisely relatively, right? Small problem sizes, right? Okay, yeah. Why skip? Because not important, okay? When the problem sizes are relatively small, when you do comparisons, the better, worse behavior won't reflect the cases when the problem sizes are large, and we want to focus on the large problem sizes, but not relatively small problem sizes. That's the meaning from asymptotic notation point of view. Okay? Yeah. The reason we get scared because, yeah, so here, let me just give you a few more reasons. Because too much distortion for small problem sizes. Okay? So here, distortion away from your formula, right? Because think about, the overhead part will make the distortion. Think about that. The overhead part will make the distortion. Okay? Yeah. So your formula, yeah, your efficiency formula, your performance formula will be distorted by certain overhead, the overhead part for smaller problem sizes. That's the reason. Think about that. Okay? Think about that. Yeah. Here I give you two views. Yeah. Two closely related views. Okay? Yeah. So with this understanding, then you can answer that question better. Yeah. Okay? Yeah. So that's the necessary information you need to answer this question correctly. Okay. All right. So let me